Hi, everyone. Welcome back. This is part 2 of 2 talks on an introduction to topology class that I taught at Brandeis University in the fall semester of 2015. Brandeis is a small research university based in the United States, and the class that I'm talking about is an upper-level undergraduate course taken primarily by third and fourth year undergraduate students. It included about 10 students in the audience. If you'd like to hear more about the broad outline of the course, the format, and so forth, that's what I talked about in talk 1. In talk 2, I would like to spend some time talking about how I went about choosing the specific topics that we covered in this course. So as a quick reminder, I had the following goals when I was designing this course. Brandeis does have a PhD program, and so that means that we do have the first year topology sequence, including a course on, say, the first few chapters of Hatcher, things like the fundamental group covering spaces and so forth. But the students who were taking this class were, well, they were finishing up their undergraduate major, and so they didn't continue on necessarily into this subsequent class. So as a result, there weren't really, in terms of topics that I had to cover, well, I wanted to make sure to cover the core topics, which I think are kind of necessary for in any introductory topology course, things like connectedness or compactness and so forth. But other than that, I really had a lot of freedom to explore, to really sort of showcase the types of places in which topology might crop up. In particular, I remembered when I was an undergraduate, the course that I had taken in topology as an undergrad really focused on point set topology for the entirety of the semester. And I was really pleasantly surprised when I went to the PhD program that I went to and realized that topology can have a lot more geometry or a lot more algebra. And I wish that I had seen that sort of thing when I was an undergraduate already. In particular, I wanted students to have an idea of the types of topology people are actively working on these days. Things that if they were to go on to a PhD in mathematics in topology, what are the sorts of topics that they might themselves end up working in? I also had some broad goals regarding the structure of the class. I talk more about this in talk 1. But of course, we will see that this will also show up in the way that the topic selection. This will also show up in this talk as well, naturally. Right. So when I started to think about designing this course, I tried to think about the core topics that every student who has taken point set topology should understand. And I came up with this list of 5 topics. I don't think this is particularly controversial. Of course, these first 3 topics are basically the main definitions: topological spaces, continuity, homeomorphisms, how to make new topologies out of given old topologies. Hausdorffness is in here somewhere, and then the notions of connectedness and compactness. There are other topics that many people do like to cover, things like Tikhonov's theorem or things like the Eurozone metrization theorem and so forth. And one can spend a reasonable amount of time talking about the proofs of these theorems. But personally, I felt that seeing the proof of those complicated theorems, well, is very nice and surely a nice experience, can be a nice experience. But I felt that could be replaced by talking about some topics that are perhaps indicative more of the places in which topology crops up or something like this. But that being said, I really wanted to make sure that we spent a fair amount of time talking about these core topics and students really understood this sort of these fundamental aspects of topology before moving on. For this part of the course, we followed the topology textbook by Moncrief. This is the standard textbook that was used in the department long before my time, and I didn't want to change that. The course had a single assigned textbook, and it was this one. And I think there's a real advantage of using a textbook that's a standard. So in particular, if you then go on into a different department, for example, into a PhD program, then there's some standard background that we can all refer back to. Then I wrote down a list. This is something I do in every course. I wrote down a list of every single class day, including the days in which we didn't have class. So in particular, there was Thanksgiving break at the end of this fall semester. At Brandeis, we also have a number of days without classes in the fall semester. So I marked these out, and I mapped out how the amount of time that I wanted to cover these core topics. And it turned out that it really only took, let's say, about half of the semester. I had planned out the midterm date ahead of time, and frankly, I had wanted to cover these core topics before the midterm, but this did not turn out to be true. I needed 2 extra class days than expected. If I teach the class again, of course, I will plan that a bit better. But of course, that leaves quite a few lecture days that I really felt like I could broaden our horizons and see the various different places in which topology can crop up. So I really felt that there was a lot of room in which we could have this exploration. The first thing that I knew that I wanted to do was, well, it went at the very end of the semester. As I mentioned, Brandeis does have a PhD program, and at the time there were 3 topology faculty present at the department. And of course, while they were all topologists, their research was not extremely well, or their research was relatively distinct from each other. And so for 3 of the last 4 class days, I invited PhD students from these individual groups to come give guest lectures in the class. So the reason I really definitely wanted to do this is because, well, part of my goal was to indicate to students what current research is like, what they might themselves work on if they ended up doing a PhD in mathematics and especially topology, and what better way than to have these guest lectures by current PhD students. As a side benefit, of course, one gets to meet said PhD students, and they were all extremely friendly and cool and nice. And I think it's a really nice experience to meet current PhD students and see that, wait, these are really cool people, and maybe I too might want to be like them someday and continue on to PhD or something. So let me say a little bit about what these guest lectures were like. The first guest lecture was by Devin Murray. He was a student of Ruth Charney at the time. This was an introduction to geometric group theory. At the time, I'd spent a little bit of time talking about groups in class as well, more about that in a second. But Devin talked to us about free groups. I had not mentioned those before, at least not in very much detail. He also introduced the notion of covering spaces, perhaps my favorite topic in topology. And he used covering spaces to give us the proof of one of my favorite facts, that every subgroup of a free group is free. So this was, I think this entire lecture is probably a distillation of my favorite facts from the next course in topology, namely fundamental groups and covering spaces. So it was really, really wonderful to be able to also have this happen in the undergraduate level Poinsett topology class. The second lecture was by Catherine Rayox. She was a student of Danny Ruberman at the time. This was an introduction to knot theory. I think this was really amazing. Just in knot theory, I think, is an extremely valuable thing for undergraduate math majors to see, in part because it's just so surprising that one can use mathematics to talk about these concrete objects like knots and links. She gave us the basic definitions of knots and links. She told us why Seifert surfaces exist. She also talked about the main questions in knot theory, things like how can you tell that 2 knots are different or 2 knots are the same, things like that. So she drew a number of really nice pictures, and it was all very, very concrete and tangible, which was lovely. And then the final lecture was by Matt Garcia. He was a student of Kiyoshi Iguse at the time. He talked to us about something I found extremely unexpected, but consequently extremely cool, maybe perhaps unrelatedly extremely cool. So Tikhonov's theorem is something that students might see just in a more standard, let's say, point set topology class. As a reminder, this says that an arbitrary product of compact spaces under the product topology is also a compact space. Personally, I had decided that I didn't want to spend too much time on that theorem because it seemed like it was a lot of work for not necessarily a ton of payoff. But then Matt came along and he gave us the basics of propositional logics. In particular, he told us things like what is a language and what are formulas and what does it mean for formulas to be satisfied or satisfiable. And then he showed us how Tikhonov's theorem can be used to prove this following result in mathematical logic, that in order to show that a set of formulas, an arbitrary cardinality set of formulas is satisfiable, it suffices to prove that every finite subset is satisfiable. So in contrast to the other two topics, this was a bit more abstract, but I really enjoyed how, well, this was extremely unexpected. And had I not had these guest lectures, there's really no way that I would have been able to explain these real diversity of topics in which topology can crop up, and by current PhD students, no less. And then finally, to cap off the semester, on the very last day, we had, there was, of course, a summary of the course. There was an opportunity for student feedback. And then I reserved the rest of that hour to talk about my own research. At the time, this was primarily based in knot theory, but maybe from more of a four-dimensional perspective. And so Catherine's talk on knot theory was a very nice setup for me to talk about my own research. Okay, so that was the very end of the semester. And I was quite happy with how that turned out. And I think the feedback from the students was also really positive on especially the guest lectures by the PhD students. But then, of course, that leaves still many days of interesting topological applications that one can try to think of. So the way I did this is as follows. So around the midterm time, just around the time that we were finishing up the core topics, I took about half of a class day, so about 30 minutes, to give a broad overview of the different sorts of directions in which we could go for the rest of the semester. And then based on that short survey and based on some resources to which I gave the students links, so internet resources that they could go look up on their own, I sent them a survey and people filled in their preferences, and based on the responses to those preferences, I filled in the rest of the schedule. Unfortunately, I ran this survey from the course management system, which I no longer have access to. So unfortunately, I seem to have lost that data. That did not expect that I would be giving a talk on that class 7 years after the fact. Here are the topics that I suggested to the students. Measured spaces are a pretty standard topic, but in case students were really interested in this, I wanted to make sure that they had the option to spend time talking about this. Dynamical systems and chaos. This is something I had been really pleasantly surprised and somewhat amused to find out that when I was a PhD student in topology, I spent less time doing point set topology than my colleagues who were students in dynamical systems. So it seemed like there was so much point set topology in this really cool research area. So I wanted to make sure that that was one of the options. Fundamental groups and introduction to algebraic topology, that's more of a preview of the next course that someone might take. At the time, I called this introductory homotopy theory. Since then, perhaps unfortunately, I've seen much more homotopy theory, and perhaps this doesn't count so much as algebraic topology. This was really focused more on the fundamental group. I mentioned in talk 1 that 3 out of 10 of the students in my class were economics majors. And one of the reasons that economics majors might end up in a point set topology class is that say some of the higher ranked topology programs, PhD programs, really want their students to come in with some kind of point set topology and especially some kind of introductory analysis and so on. And it turns out that fixed point theorems are really relevant in the study of economics. And one can use these really fundamental point set topological notions to prove interesting results in game theory. In particular, one can prove Nash's theorem about the existence of equilibria in standard games. So since there were economic students in the class, I definitely wanted this to be one of the options available as something we could dive into the rest of the semester. And then finally, as a low-dimensional topologist, I really wanted to spend some amount of time talking about manifolds and potentially talk about the shape of space, etc. One of the aspects, of course, of having these many options is that these are not necessarily covered in one textbook. So I didn't want to force students to buy multiple textbooks, in particular if I didn't know ahead of time what sorts of topics I would end up covering in the class, since that was based on the vote that I ran with the students in general. So I wanted to, so there are two aspects of this. One is, as a person who's not necessarily an expert in all of these things, I needed to find something that I could follow to write my lectures based off of. And on the other hand, I also wanted to have something concrete that I could give to the students so that they weren't just following my lectures, and they also had something that they could individually understand on their own, rather than just based their entire learning on the lecture notes. So the books that I personally ended up following mostly was the book by Adams and Franzosa. This is Introduction to Topology, Pure and Applied. I quite like this book. It has a variety of these applications in the second half of the book that is extremely useful. For this introductory algebraic topology material and the manifolds material, I used the book by Lee, Introduction to Topological Manifolds. And for the bit about dynamical systems, I used a book by Bryn and Stuck. Right, so these were the options that I gave to the students, and these were the resources that I wanted to use, of course, depending on how the students voted. There was a snag in the process. I had really expected that there would be some sort of obvious choice, perhaps, that there would be an obvious preference of 2 to 3 topics that I would then delve into in a reasonable amount of detail. But really, every topic had some interest from students. And consequently, I didn't really feel comfortable just ignoring some of these topics when each topic had substantial interest. And so what I ended up doing is I ended up covering all of these topics, but I varied the length of time that I spent on each topic based on the interest that I had from the students. And again, I really wish I could show you the data from the survey that I ran, but unfortunately that is lost to time. That being said, here is what the final schedule ended up looking like. Metric spaces were popular, but not that popular, so they only got 1 day. Dynamical systems were quite popular, so they ended up getting 3 days. Same for introductory algebraic topology, fundamental groups, etc., as well as game theory, Nash equilibria, and so forth. And then, surprising to me, manifolds didn't end up getting that much interest. I had really wanted to spend 2 days talking about manifolds rather than the single day I ended up spending on it. But unfortunately, what happened is that I ended up spending a bit more time on these topics than I really intended. And then I ended up having to sacrifice a manifold day in order to fit in as much of these previous topics as I wanted. One of the students commented to me that they voted rather on these topics because they felt that they could learn about manifolds in their subsequent topology class, whereas they would not necessarily have an option or an opportunity to learn about fixed point theorems in game theory or dynamical systems in a topology class subsequently. And so they ended up voting rather for these topics that are not as topological, just because they wanted to have an opportunity to see it. which I found to be an interesting consideration that I had not thought about prior to running this survey. I wanted to tell you a little bit about how some of these topics went. There was a real challenge in that I am not an expert in dynamical systems. Otherwise, I would be talking at a dynamical systems conference instead. I had spent some amount of time as a PhD student learning about dynamical systems because they are, in fact, extremely cool. So I spent 3 class days talking about dynamical systems. We began by talking about the basic definitions. We talked about orbits and fixed points and periodic points. What does it mean for dynamical systems? How do we relate them to each other? That's the notion of conjugacy and semi-conjugacy. We had lots and lots of examples. That was true throughout the entire course. We talked about the definition of chaos. If you look at the definition of chaos, I mean, that is just a point set topological definition. I mean, every person that has taken a point set topology class should understand that definition. And so it really didn't need so much extra material to really understand this. And I would say it's really more of a matter of most people just don't get the opportunity to see these interesting places where topology crops up rather than needing so much buildup and so forth. And then we talked about lots of examples. We talked about how chaos behaves under topological conjugacy, and we talked about what chaos means versus something like randomness. And that takes up a nice 3 hours of class time. And at the end of that, in the corresponding problem set, students can really work on problems that are perhaps really elementary dynamical systems, but it does require point set topology, and it is still an introduction to an interesting place in which topological ideas and topological notions can crop up. So in order to work on this problem that I have here on the screen, you don't really need much more than what you already know as an undergraduate point set topology student. The other special topics that we talked about, you've already seen on the list of topics on the course calendar there. I especially like the game theory discussion in particular because it really catered to the economic students. And as I mentioned, there really isn't an opportunity for topologists to see this unless you explicitly go off and take a game theory course or something like that. I really like the chapter 10 treatment in Adams and Franzosa for this. Metric spaces, the shape of space, fundamental groups, manifolds, these are perhaps more canonical topics that most people in topology have really thought about. And these are very nice sources for this sort of thing. But even for something like metric spaces, you can really have interesting problems that students can work on and find interesting. For example, here, instead of thinking about, let's say, the Euclidean metric, not so exciting, you could think about the Hamming distance on vector space on the space 0, 1 to the n. And you can come up with this interesting question. This really comes out of Adams and Franzosa, which is not just obviously point set topology, but it uses these point set topological notions in an interesting and cool way. I wanted to end by talking about some of the challenges that this approach presented. The first challenge was really about expertise. So when I embarked on this adventure, I was really excited. I thought it was a great idea, otherwise I wouldn't have done it. And in part, I wanted to learn all of these interesting places where point set topology crops up. But it required more work than it would have if I were just talking about things I already knew. As a result, because I just didn't have the expertise to begin with, it required a fair amount of work to just sort of get up to the level at which I could talk confidently about whatever topic was the topic of the week. One thing I really feel that one thing I feel really conflicted about is the trade-off between depth and quantity. On one side, I really wanted to showcase the variety of places in which these point set topological core topics crop up, but that's on the level of quantity there. But because I couldn't bring myself to choose some of the topics rather, since the survey was somewhat inconclusive, I wasn't able to go into as much depth as I would have liked. And so I feel like perhaps if I had chosen a smaller set of topics, more could have been done. Ultimately, I think it was fine, but it's something that I feel conflicted about and perhaps could be done better. Other problems are sort of, well, first of all, it was difficult to assign these problems without having students have access to corresponding textbooks. So I was using a variety of different sources and they all had different notation. And I was posting scans of these materials on the course management system, but it was really difficult to keep track of all the things. And so just logistically, that was quite challenging. And moreover, because we were using lots of different textbooks, you also had to keep track of a lot of different errata. And perhaps you saw this in the previous slide. One of the problems which I had taken from one of these textbooks had an error in it, which I didn't realize until much later because I was just trying to keep track of too many textbooks at the time. So it's a bit of a challenge to come up with appropriate problems, and then it's just a logistical challenge to keep up with a lot of different sources. This is, of course, something that will get better if one does it more than once, but certainly in the first iteration, it was a real challenge. Thank you for watching.